So in the previous lecture, you have seen this. We have seen the message signal, and we saw this dy dt of mt of the message signal. That means the differential of the message signal. We drew these two. Uh, First, we obtained this was the message signal, and then we obtained dy dt of mt, and then from there we obtained the phase modulated signal and frequency modulated signal, FM, PM, and FM. And in the phase modulated signal, we saw that there will be two frequencies because dy dt of mt was having, yeah. So and then we saw frequency modulated signal. So because the signal was changing linearly from time t1 to t2, okay, so that's why frequency was also changing linearly from time t1 to time t2. So if I now see in here, so then this in this portion, the frequency increases in this portion, linear increase in the frequency of the, this is from fmin to fmax. Yeah, this is what we obtained in the last lecture. Now in this lecture, we want to again see frequency modulated signal and then see its bandwidth. Okay, we wanted to calculate its bandwidth of the frequency modulated signal. That means first we wanted to obtain the spectra of the, how is the spectra of the wideband signal going to how is the spectrum of the FM signal going to look like, and then based on that we wanted to classify it whether it is going to be a wideband signal or a narrowband signal. So the phase and the frequency modulated signal that we have obtained earlier. So we are going to write it again, and then we will write that signal in the form of the phasor form. In the phasor form. So what was the signal that we have obtained for the frequency phase modulated signal? So we have said this 5 p.m. What was this 5 p.m. T? What was 5 p.m. T? What was the signal? Anyone can help me out? Yeah. Sonu, do you remember?
2 pi fct. Sir, a cos pi fct.
Is a pi fct.
A cos.
What? A then
Cos.
cos what? Yeah, I'm. Your voice is not audible.
Sir, 2 pi fct plus kp of mt.
F-
Kp into mt.
fct plus kp of mt. Correct. This was the signal. I will just say this thing as AC. Okay. So this was the phase modulated signal. Hmm. So this was the phase modulated signal. And if I want to write this thing in the phasor form, this was the phase modulated signal. And if I want to write this in the phasor form, as where I say that 5 p.m. at t is nothing but, I can write this thing equivalently as in the form of the iota as e to the power j 2 pi fct plus kpmt. Can I write it like this? Can I write this above equation like this in the phasor form? So then in that case, what is the relation between the PM signal and the phasor form of the PM signal? What is the relation? How should I write it? What should I write in here addition? What is the relation between the two of them? how should we write 5 p.m. bar? How should we write 5 p.m. in terms of 5 p.m. bar? What should I write here? Anyone? Yeah. Priyanka, what do you say? What should I write? Priyanka, am I audible? Priyanka, am I audible?
Sir, excuse me, sir. We only take real partner because they are real and imaginary. Both parts are present in phasors.
Mm-hmm.
So we only take real parts because the
So what you are suggesting is that in here, what should I write? I should say real part of this. Is it?
hmm, yeah, sir.
Correct. Correct. Yeah, this is what the answer I was looking for. So I can, if I just say real part of this, then I can write this above 5 p.m. bar as this. Okay, fine, fine. This is what I was looking for. A simple answer. Hmm. Yeah. Similarly, if I have to write the same thing for the phase modulated, sorry, frequency modulated signal, then what should I say? Similarly, similarly, I can write for frequency modulated signal as well. So what should be that? So if I, so first of all, what is the FMT signal? Yeah, Prakash, do you remember what was the FM modulated signal? Prakash, are you there? Prakash Manloi. Prakash Manloi, are you there? So you have joined. Okay. Prakash, are you able to hear me? So I see a lot of people have joined, but they are not responding. That eventually says that they are not present. Okay. Anyone else? Anyone else who remembers the expression for 5 FMT?
Sir, A cos
Mm-hmm.
2 pi
A
FCT
cos 2 pi FCT.
plus KF of integral
Correct. Go ahead.
plus KF of integral 0 to t m of t d tau.
Yes. So this was who?
Pujita sir.
Pujita. Yeah. Good, good, Pujita. So what Pujita is saying, we can write this thing as, so I will just say AC. Okay. Instead of A, I will say AC and then I will say 2 pi FCT plus KF times integral minus infinity to T and MT dt like this. And what I will do, I will define this complete thing as AT. I will define this complete as AT, and then what we can do, we can write this thing equivalently as said by Pujita. We can just write this thing as 2 pi FCT plus KF times AT. Okay, where AT is nothing but the integral of the MT dt. So just to simplify things, I have just written it like this. So this is again, let us say this is equation number 3. And now if I want to write it in the phasor form, so I can say this phi fm t should be what? AC times e to the power j or 2 pi fct plus kf at. Kf at. And we know this time that where phi fm t is given by the real part of phi fm hat t. Phi fm hat t. Okay, so this is what we have said in here, and this can be said as equation number 4. So far, so good. Anyone have any doubts? This and this, yeah. So these two are the equivalent phase form representation of this. So now, what we want to do in here is, before we go ahead with the this equivalent. Okay, let's go ahead with that. Okay, let's go ahead. So if I've said this thing, phi fm is real part of phi fm hat t. So let's now put this thing and then try to understand it well. So if I now say this fm is, so now let's solve this thing. We will get what? We will get real part of, I'm just going to put phi fm bar, phi fm hat t in inside this. So this is what AC e to the power j 2 pi fct plus kf at plus kf at. So now I want to rearrange this thing in terms of, I want to separate the carrier frequency component from here and the remaining terms. So AC being real, we can take this thing outside and let everything be inside, and I can write this thing as this, what, e to the power j, not 2 pi. I want to separate, okay, let it be 2 pi fct times e to the power kf at. Any confusions till this point? Anyone? Any doubts? Okay, if not, then I will just rearrange this and I will say real of, and I will take the e to the power j 2 pi fct the other way around, or probably I can switch this thing in here as well. So I can say, okay, yeah, so this is what I can say. Now, I can take the e to the power j 2 pi fct to the one side, and then I can expand this, the first term. I can expand the first term. So what will be the expansion? Do you people remember the expansion of e to the power x? What should I write in here? What should I write in the
1
bracket braces?
e to
Yeah,
the
go
power
ahead.
is 1 plus
Mm-hmm.
k into a of t by 1 factorial plus,
Okay, so I should be saying 1 plus j k f a t. Is it the first
yes
term?
sir, yes sir,
What should be the second term?
square by
Minus
2
or
factorial
plus?
plus sir,
Should it be plus?
yeah,
Okay. Then what?
square of this term by 2 factorial,
Kf square by 2 factorial, and then a square t.
hmm.
Yes, what next?
And then for cube of this term by 3 factorial similarly.
Yeah. So let me just make some space. Okay. So I will just say dot 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 like this. Is it? Yeah. So now if I have to write this thing equivalently, if I take the real part of this thing, and multiply it with the e to the power j 2 pi f c t and then start writing it. So what should I get now? So what I'm saying is, if I want to solve this thing further, phi fmt, what should I get in here? If I
Excuse me, sir.
multiply, yes, go ahead.
Yes, the third term will get negative because j squared
Negative,
get
yeah.
minus 1.
Yes, this is what I was waiting for. Yeah. So there is going to be a negative in here. Yeah. So that is fine. So now, so if I now want to multiply this e to the power j 2 pi fct with this expansion of if we want to multiply this term this term with the expansion of this, which is this. Okay, so what, and after that we take the real part of it. What will we will get? What should be the first term? What should I get? So if I write this thing, so AC would be outside, and if I take the real part, so e to the power j 2 pi f c t multiplied with 1, this multiplied with the first term will give e to the power j 2 pi f c t, and if we take the real part of that, then we will be left with what? We will be left with cos 2 pi f c t. Yes or no?
Yes, sir.
We will be only left with cos 2 pi f c t. Similarly, yeah, Gayatri. So similarly, what should be the other terms? So the next term after taking the real part would be what?
Minus k square into a square by 2 factorial
Minus
into cos phi.
k square, because there is one kf, and if I multiply with this with e to the power j 2 pi f c t and take the real part,
Sorry.
it should be only one kf and then at, and as we are taking the real part of it, and there was j, so shouldn't it be sine 2 pi f c t?
Sorry, sir. I missed that second part.
Yeah. So similarly, so what I'm trying to do in here is, so we will get a series of terms. So I will just write these terms. So the next part would be kf square times factorial 2, kf square times factorial 2, and this would be what? A square t, and this will be a cosine term, cos 2 pi fct, and plus so on, we will have multiple such terms. Okay. So is this part clear to everyone or not? Anyone who has not understood this? Anyone who has not understood writing this part, this equivalent step? Anyone who has not understood this equivalent step? Okay, everyone, have you understood this thing? Chalu, Tanvi, Prakash.
Yes, sir.
Okay, good, good. So yeah, so now if I see these individual terms, what can we say about these terms? So if I see these individual terms, okay, let me just shift it a little bit. Yeah, okay. If I see these individual terms, so what can we say about these? If I see the individual terms, so they have a very strong resemblance. They have a very strong resemblance with our. So if I see this term, if I see the first term, if I see the first term, so this has resemblance. This is exactly what? This is the carrier signal. Yes or no? This is the unmodulated carrier. And what is this term? How? What is the? Do we have any resemblance of this term? So if I assume that KFAT to be some message signal, so then this is what? If I assume that KFAT is empty, okay, if I assume that KFAT is some message signal, KF is a constant and AT is what? AT is the integral of MT itself. So then this has got very strong resemblance with which signal? This is with signal. Yeah, Shalu says DSB. Yes, correct. So this is DSB SC signal. Yes, so this has got very strong resemblance with DSB SC signal. Similar to DSB-SC. Okay, similar to DSB-SC. Now, similarly, if I see this part, if I see this part, if I see this part, what can we say about this? What can we say about this? So this is similar to DSB-SC with AT as message signal. And what can we say about the third part? What can we say about the third part? What can we say about the third part? Anyone? Anyone can tell me? Anyone? What can we say about the third part? Chalu, you said the first part was DSB-SC signal. Okay, if AT is a message signal. Now, what can we say about the second part, a third part? What can we say about the third part? I'm still waiting for an answer. Chalu says no idea. Okay, fine. Now let us say this way. If I say that this complete term on the left, that is kf square by factorial 2 into a square t, let this be something as ct, some signal as ct. Then in that case, what can we say now? If what I'm saying is,
Modulated signal.
if I assume this thing to be ct, yeah. So what can we say about this? Yes, someone said something. Who was
Temperature
that?
modulated signal. I'm guessing, sir, only.
Yeah, so that is fine. If Ct is the signal, in that case, if you multiply Ct with cos 2 pi f Ct, what we will get? We will get again a DSB-SC signal. If we assume that Ct is now the equivalent message signal, okay, if we assume that Ct is the equivalent message signal, in that case, again, this will be a DSB-SC signal. So this will be similar to DSB-SC with 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 I will say a square t, because kf square by factorial 2 is a constant. So I'm saying that with a square t as the message signal. Is it or not? Do everyone agree with these parts, what we have just now said or not? Anyone having any doubts? Yeah. How about Chalu says she has understood it? How about others? How about others? Everyone is on the same page. Are people able to follow this part? Good, good, good. Now the next thing that we want to calculate is, we now know this Fm can be written as the summation of these DSB-SC signals, okay, or a summation of this DSB-SC plus the unmodulated carrier signal. So if I have to calculate the bandwidth of the message signal, if I have to calculate the bandwidth of the message signal, then what can we say about it? Okay, so we knew that if uh, so for that, we have to find the relation between MT and AT. Okay, we have to find the relation or the bandwidth relation between MT and AT. So if I say that MT has got a Fourier transform of MF, and say that the MF is band limited to B hertz, say MF is band limited to B hertz. So I'm saying in other words that the bandwidth of signal MT is B hertz. Okay. If that is the case, then integral of MT, then we knew that AT is nothing but integral of MT. Integral of MT dt. So what I'm asking is, if I take the integral of MT and say that AT, the Fourier transform of AT looks like capital AF, so then in that case, what should be the bandwidth of AF? Can anyone highlight this? Can anyone highlight this? This would be band limited to, can anyone highlight this? Can anyone highlight this? If I take the integral of MT, okay, and then we calculate, then we represent it in the, so if we take the integral of MT, which is AT, and now if I want to take the Fourier transform of AF, so what should be the maximum frequency component in AF? Or simply, if you see this expression, you knew the maximum frequency component in MT is B hertz. So if I take the integral of that, what should be the maximum frequency component in the integral of MT? Okay, let us, is the question clear to everyone or not? Anyone who has not understood the question? Is the question clear to everyone? Is the question clear to everyone? Okay. So yeah, if the question is clear, so the question, so what we are saying is that if we have MT, okay, and that was B hertz, that was band limited to B hertz, that means the maximum frequency component in MT was B hertz. Okay, so in that case, what should be the maximum frequency component, the integral of B hertz, integral of MT? So if we start off with this signal, in here, we knew that let this be MT. If I say that this rectangular pulse is MT, and we knew that this is the integral of, the triangular pulse is the integral of the rectangular pulse. Okay, so if this was having a maximum frequency component of B hertz, then what should be the frequency of this, maximum frequency of this signal? What is that? Are people able to follow the question that I'm asking? So let the message signal, let MT be this. Okay, I'm saying let MT with this be MT. Let this be MT, and in here, let this be MT. So if we take the integral of MT, this is integral of MT. So MT was band limited to B hertz. So what should be the what should be the bandwidth of integral of MT?
Remains same, sir.
Yes, it remains same. Yeah, correct. I see multiple people writing the same. So a similar example can be, we can take it of a sinusoid pulse, a sinusoid waveform, and if we take the integral of that, we get cosine. So what we are effectively saying is that if we take the integral also, even in that case, this will be, so this will be band limited to, again, same B hertz. I hope this is clear to everyone. Yes or no?
Yes, sir.
Yes. So if this is clear, in that case, so if the message signal is band limited to B hertz, then what is the bandwidth for the DSB SC signal? What is the bandwidth of the DSB SC signal? So I will put this thing little down. Yeah. So if if the message signal is this AT is band limited to B hertz, then in that case, what is the, so if I say not, so I will say it like this. Okay, let us say not AT. I say AF has got bandwidth of B hertz. So what should be this DSB-SC signal? SC signal of the same will have the bandwidth of, because it has got lower and the upper side bands on both of the positive and the negative frequencies. So the equivalent bandwidth is 2B, correct. The equivalent bandwidth is 2B hertz. Okay, the equivalent bandwidth is 2B hertz. Fine. We have obtained the equivalent bandwidth of the first term, the second term. So now what we want to do is we want to obtain the equivalent bandwidth of the third term. Now in the third term, what we have said is that we are saying that the equivalent message signal is A square T.
So can you repeat how it's 2B for DSBC?
That is the case now. So if we so if the message signal is like this, if the message signal was in here like this, so in DSBSC signal we get two such.
Yes, yes. Okay, I got it. Sir.
Yeah, so the overall bandwidth will be twice of the original bandwidth of the message signal. Yeah, I have said DSBSC. Yeah. So in DSBSC, the overall bandwidth is 2B. If the message signal has got bandwidth of B, then DSBSC signal has got the bandwidth as twice of the message signal. Now, in the third term, if we look actually, so what is the bandwidth of the message signal? Now, the equivalent message signal for the DSBSC signal in here is A square T, not AT. Yes or no? Equivalent message signal in here is A square T. Now, if this is A square T, I can write this thing as AT times AT. So if I see in here, now I will do a partition. We knew that AT, okay, AT in here is nothing but, so we have already said that MT and AT will have same bandwidth. Okay, this is clear. Now we wanted to go ahead one more step in here. So what we want to do is we want to calculate the bandwidth of A square T, and A square T is nothing but AT times AT. And if that is the case, if I take the Fourier transform of this, I will get what? I will get AF times AF. Is it? What should I get? If I take the Fourier transform of AT times AT, what can I say about this in terms of the frequency domain, in frequency domain? What should I say?
Convolution.
Yes, I should be saying convolution. So I will write it a little compact. I should be saying this convolved with this AF. Now we knew that AF has got bandwidth of B hertz. So in that case, AF convolved with AF will have bandwidth of what should be the bandwidth of this? So what?
2B.
Yeah, Gayatri and other people. So someone said 2B. Who was that?
Sarakas.
Akash. Yeah. Why do you say 2B? Because if we take convolution, and because one signal is slided and summed with the other one, so effectively, if I see that the bandwidth will be band limited to B hertz, is this thing clear to everyone or not? Anyone who has not understood this part, that this signal will be band limited to 2B hertz. Is this point clear to everyone? Anyone?
So I didn't understand. I didn't understand.
Okay, so Toshika, so if you take a signal, okay, and supposing you had this rectangular pulse. Okay, let us take the same example of the previous case. Yeah. So if you had this rectangular pulse and you convolve with the same rectangular pulse, what would you get? Do you recall? What would you get? Or instead of having this complete rectangular pulse, let us only assume a unit, a wave which is only going from 0 to t. Okay, so let the message signal be only positive, only one cycle, that is between 0 to 1. Let us say 0 to 1. In between 0 to 1, it takes this value. Rather, let us do it again. Okay. I said this is the message signal between 0 to 1. Okay, let this be AT. Let this be AT. And if I do AT convolution with AT, what should I get? So the convolution of two rectangular pulse or two square waves will be what? Toshika? So if I convolve this with
Yes, sir.
another rectangular pulse of same time duration, what should I get? So if I do AT, so this is written in F. Yeah, so let us say AF. And if I do AF, convolve with AF, yeah, what should I get? If I do the convolution, what should I get? Do you remember?
No, sir, I don't remember. That's why I asked.
Okay, so if you don't remember, in that case, can anyone else help? What should be the resultant output? What should be the resultant
Similar
output?
graph but with double frequency.
Yeah, so what we will get it like this. So this will be maximum when, so if I see AF convolved with AF, what will happen? We will fix one of the plots and then we will shift this from left to right, yes or no, and then do the integral over it. So if you keep on shifting, so at when it is exactly overlapping, it will have maximum area. That area would be what? The multiplication of the two and the integral that. So what should be that? So it will have maximum area. So otherwise it will have to the left and to the right. When it is from in this region, it will be increasing like this, and when it goes away further, so it will keep on decreasing. So this is how it is going to look like. But so this is going to be, if this is 1 and 0, and then this should be 2, in that case it is going to be like this. So that's why the total bandwidth will become twice of B. Okay, I hope this is clear to everyone. Yeah, so if you're still unable to get it, I will say just take this simple example and do the convolution. You will get it.
So understood, sir.
Yeah. Okay. So then this message signal A square T will be band limited to 2B hertz. So if this is band limited to 2B hertz, so then in that case I will write it A square F. That means, sorry. Oh, probably, yeah. AF convolved with AF has the bandwidth of 2B hertz. Then in that case, what should be the DSBSC signal bandwidth? What should be the DSBSC signals bandwidth?
4B.
It should be 4B. Yes. It should be 4B. Now, I haven't done the same for the next terms. So if I keep on seeing in a similar fashion, what do we get? So the next term will have bandwidth which is again more than 4B. And it will keep on increasing. So if I calculate the overall bandwidth, the sum of all of them, what is the bandwidth of the modulated wave in this case? Will that be band limited?
Sir, it's increasing in the power of 2. So
Yes. So it is increasing in the power of 2. So this is surely not band limited. So theoretically, so what is the overall bandwidth of the FM signal?
Infinite.
Infinite. Yes, yeah. This is what I'm coming on to. So what do we have just now concluded? That the modulated signal wave is not band limited, and hence has infinite bandwidth, infinite bandwidth theoretically. Yeah. Okay, it has got infinite bandwidth. So, but we cannot work with a signal which has got infinite bandwidth. There is no way in which we can work with a signal which has got infinite bandwidth. So what we will do, excuse me, so what we can do approximation of that, okay, and neglect the higher order terms, so that we can work out, we can come up with a frequency modulated or the phase modulated signal which is workable, which is implementable, which is realizable. Okay, so instead of considering all these terms, if I consider all these terms, then the equivalent bandwidth is infinite. So we don't want bandwidth to be infinite, because again, otherwise we cannot do the transmission and the reception for the infinite bandwidth. So if I want to make it more realizable, so then in that case, I will put a constraint. I will put a constraint such that we can neglect higher order terms, and that constraint that we put is, we assume that let this mod of, okay, let me just give some space. We assume that this mod of kf at is small. Okay, so if I assume that kf at is small, then what I can say, I can neglect these higher order terms. I can neglect all the other higher order terms. I will only consider this term, and then all these higher order terms I can neglect. I can assume them to be going to 0 like this. Okay, so if I do that, then in that case, this signal phi fm, what is now equivalent phi fm signal? This becomes AC, the carrier wave, the unmodulated carrier, cos 2 pi fct minus kf at sine 2 pi fct. Now, just now what we have seen. Now this is, if I see this, so this is linear modulation. This is linear. The above one was non-linear. So this becomes, because of this approximation, this becomes linear modulation. And what is the bandwidth of this FM? Bandwidth of this FM signal
2B.
is 2B. Yes, correct. So because its bandwidth is 2B, we call this thing as narrow band FM. We call this thing as narrow band FM, and this approximation gives us to the narrow band FM. Okay, so that means in here, what are we doing? We are neglecting higher order terms. Okay, we are neglecting higher order terms. Yeah, so then in this case, bandwidth becomes 2 bHz. And similarly, we can adopt a similar process for the phase modulated signal, because the same is going to happen for the phase modulation as well. Similarly, I can write this phi PM phase modulated signal approximately as AC cos 2 pi fct minus, in here, what will be the difference? It should be minus kp times what? In here, there will be mt itself, the message signal mt itself. Instead of at, which was integral of mt, in the phase modulation, we have direct mt. Yeah. sine 2 pi fct. Okay, so these will be the two signals in here. Now, are these points clear to everyone? Anyone who has not understood this? Narrowband FM and uh, the narrowband phase modulated signal. So what are everyone understood this? Anyone who has got any doubt on these parts or any questions? This should be 4 and 3, and they both are again linear modulation now. Initially they were not linear; these were non-linear expressions. These are non-linear expressions, but because of this approximation, what we have done, we have made them linear. Okay, we have made them linear. So I will just quickly wrap it up by defining few more things. So if I want to calculate this power in phase modulated or frequency modulated signal, what is that? If I want to calculate the power in this narrowband FM and power in the narrowband FM or PM signal, what is that? So if I do the square of the signal and then do the integral of that in a particular cycle, what should I get? What is the power? What is the power? What is the power? So the power in this, I'm not going to solve this thing. This is again, you have to solve it. It is just again the mathematics, nothing more than that. This is AC square by 2. The power in this signal would be again AC square by 2. And in here, the modulation index is defined as the modulation index for this case. We have seen the modulation index for the AM case. Do people recollect what was the modulation index in the AM case? We have defined it by mu, and we said MP by AC. Yeah, correct. MP by AC. Yes. Pujita says MT. Yeah. Similarly, in here we have the modulation index, and that is defined by beta, and that is given by the similar formula. But in here, because that was amplitude modulation, so we were calculating how is the difference upon the overall amplitude of the carrier. So in here, what we will do, we'll calculate the same in terms of frequency, beta. So we will calculate this as deviation in the frequency upon the frequency itself. Okay, and so how do we define delta F? How do we define delta F? So maximum frequency deviation is defined as maximum maximum frequency deviation given by delta F is given by what? It is given by the maximum of the instantaneous frequency minus the carrier frequency. Okay, this is how maximum frequency deviation is given. And similarly, modulation index for phase modulation is also defined. That is defined in terms of maximum phase deviation. Maximum phase deviation, that is defined as del theta, and that is again given by the maximum deviation between theta I and the instantaneous theta I and 2 pi fc. Okay, whatever is the maximum between the difference of the two. Okay, so this is how we define the phase deviation. So similarly, modulation index for phase will be defined as del of theta upon the complete theta. Yeah. So I will stop at this point. If you have any questions, you can go ahead and ask. Otherwise, we can wrap it up.